Okay, so let's start then.
Yeah, it has started recording. We can start.
Sure. Okay, so welcome back again. And let's first, next 10 minutes, we will try to finish the topic which we started. So we are discussing about the superconducting charge qubit. And if I revise what we discussed quickly, then in the first situation, when I talk about a normal LC circuit, that is nothing but just an inductor and one capacitor. Everything is made of superconducting. And in this case, we see that the potential is going to be a perfectly parabolic and the energy levels are equally spaced. And that is the problem. So this equally spaced cannot be used, not usable for quantum computing. Then we said that we have to make, and in this case, the Hamiltonian was actually equal to q square by 2c plus phi square by 2l. So this Hamiltonian was proportional to phi square. So that's why this expression or this kind of LC circuit we cannot use in for the purpose of our case. Then I said that what we can do, we can use a Josephson junction. So instead of using inductor, we can use Josephson junction, and then of course a capacitor here. And in this case, you can see that the Hamiltonian comes out to be again q square by 2c plus. But because of this Hamiltonian, this LC circuit is including this CJ and LJ, and this is nothing but one inductor and one capacitor, that is the CJ and LJ. And because of this, the energy is going to be a non-linear. And this non-linear energy is going to make it useful for our case, because then, if you remember, then this is the UJ phi, and this was equal to -4 times EC and del square by del phi square and minus EJ
cos
into cos phi. So this is the non-linear. And because of this non-linear behavior of the potential, you can see that generally the potential is always parabolic. But in this case, the potential is going to be a non-parabolic. Like this way. So here these levels are not equally spaced. And now this system is useful for quantum computing. So if you want to use, you want to make a qubit based upon the quantum superconducting, then you have to use the Josephson junction. No? And then this system is going to be of a different types. So I mentioned that key, the one particular category which we're going to specify, that is called a charge qubit. And in the charge qubit, what we do? So in the charge qubit, we have this Josephson junction, and then one capacitor. And then we have a coupling capacitor here, that is called gate capacitor. And then we connect with some DC power supply. So this is the overall circuit diagram for the case of charge qubit. So, and we discussed that key when you apply some voltage, how some charge going to induce on this plate, and this charge we call as the Ng, and this Ng equal to Cg and Vg divided by 2E. So this is the induced charge. And this induced charge is going to shift the potential energy. And as a result, now if you look at with the charge qubit in the picture, the Hamiltonian is going to become 4EC and N cap. Just a minute. I need to start charging my system. Yeah, okay, good. So this is N minus Ng and whole square and minus Ej into cos phi. So this is the Hamiltonian we get at the end. And then I said that we can just make this Hamiltonian symmetric because, and that symmetric Hamiltonian, what is called H minus E average I. And this H dash then look like a minus 1/2 sigma dot B. Which is similar to our spin Hamiltonian, which is nothing but minus gamma H cut by 2 sigma dot B. So yesterday we discussed that because of this similarity, the whole qubit system in our case is actually going to behave exactly like a spin qubit. And then, and this BE is, in this case, is called the fictitious magnetic field. And we also saw that this B and the BE has a relation, that is the BE upon gamma H cut. Clear? I hope so, this part up till here. And then we said that depending upon the value of the VG, no? So this value of the VG will decide, okay? So I said that, for example, if the VG is going to be a 1/2, a special case, I mean, sorry, NG is a half, let us say. Technically, the Vg is going to be uh, a E upon Cg. So at this voltage, if you calculate the this energy that is called energy separation, ECC, and 1 minus 2 Ng. So this energy is called the energy gap between 0 and 1 state. So you can see that this part is going to become 0. And it means both the states are degenerate, means 0 and 1 are degenerate in this case. And the Hamiltonian particularly is going to become equal to 1 by 2 and 0 minus Ej and minus Ej and 0. That is equal to minus Ej by 2 into sigma x, or equal to minus 1 by 2 sigma x, sigma y, sigma z into Ej 0, 0. And it means that this is the BE part. So the BE is simply equal to Ej into x cap. And I told you that in this case, then let us this is x direction, y direction, and the z direction. So in this case, this spin, okay, I mean normally when the in normal situation, this BE in normal situation, this BE is equal to Ej x cap plus E z cap. It means in the normal situation, x, y, and z, this Bj is in some direction, but in the xz plane, where the one component here and another component is here. So one component this side is called Ej and this component is called Ee. But keep in mind that this vector is in the xz plane. But whereas in this situation, when you talk about this situation, so here this vector is exactly along the x-axis. So in this situation, the vector is exactly along the x-axis, and it means when you calculate the eigenstates of the H dash, okay, are is going to be then plus and negative. So plus means 1 by root 2, 0 and 1, and negative means 1 by root 2, 0 and minus 1. So you can see that if I keep voltage on the gate is just equal to E upon Cg. So in this situation, this fictitious magnetic field that will lie along the x-axis, and in this situation, the Hamiltonian is going to have this shape, this equation, and the eigenstate of these Hamiltonians are nothing but a plus and the minus. Okay, it means it is going to produce a superposition state. And I also discussed that if this Vg, or maybe I can say, so technically, if I can say if Ng equal to 0, okay. So in that situation, the Vg, I mean, is only possible when it's become 0. And in this situation, this B, the eigenstate you're going to get is only a 0 and 0. And if Ng equal to 1, then Vg will be a 2E upon Cg. So in this state, the eigen will be 1. And if Ng become half and Vg will be E upon Cg, then this is going to be a plus or minus. It means in this situation, you're going to get a superposition. So just by changing the voltage applied on the capacitor, okay, you can create a zero state or one state or a superposition state. So it is same like a spin case also. The way the spin is up correspond to 0, spin is down correspond to 1. And if spin is in between, then that is correspond to a state this or this. So you can see that by changing the voltage, okay, we can create these quantum bits. Okay, even we can create a superposition also. That is the one advantage actually you have in the case of a charge qubit, that without using the EM waves or microwaves, you can create a superposition. And so technically, to produce or to create superposition, we need to change Vg such that Ng becomes half. But the point here is that by applying a specific DC gate voltage, that is a Vg. This, of course, Ng, that is the Cg Vg upon 2E, is going to be fixed. So by applying a specific gate voltage, we can create only one type of qubit. Either it can be a 0, either it can be 1, or it can be in the superposition state. So by changing the this one, you can create only one type of a gate here. So once the Vg is fixed, and one more point I mentioned, forgot to mention that this position, okay, where this superposition state is achieved, so this Ng is equal to half. This is also called a sweet spot. Now, in reality, if you want to change the gates, okay, so what we do, we apply. So in order to achieve or create different gates, we apply microwave. So what this does then, this Vg is no longer a Vg only, okay? So Vg plus V microwave. So this is actually equal to Vg plus, let us say, V naught into sine omega RT plus phi naught, let us say. So this omega R, or I can say delta E, equal to H cross omega R. This is microwave energy, microwave photon energy. This is always equal to qubit energy gap. So when you're going to apply this energy, okay, then this is going to make a transition, okay, between the 0 state and the 1 state, same like a. And now it depends again whether you want to put a pi pulse, then pi pulse is going to create a poly X gate, pi by 2 pulse. I mean, if you keep the, let us say this Vg equal to 0, then you can create a state in the 0 state. or maybe in the one state. And after that, you can create a pi pulse or pi by 2 pulse. This is going to create a plus and the negative, or any other situation you can create. So this microwave we couple with the gate capacitor, okay? And from there we can change it. So actually what happens is exactly that this time dependent, okay? This time dependent voltage going to shake the potential of the landscape, okay? Uh, I mean, at the location where this island is formed. So this is the island. So what happened that when you're going to apply this RF frequency, then the potential at the island, okay, this is going to change. Earlier, what is happening with the application of VG voltage, you are either pushing more qubit there or not pulling qubit out of that. Okay, so you can create you can create one extra qubit there, or maybe zero extra qubit there, or maybe you can create two qubit there, or maybe no, you can create a minus one qubit, means you can reduce one out of normal. So what is happening here that when you apply this RF voltage, so this RF voltage is going to change the potential landscape here. Okay, so this potential, this is also causing potential because of the positive charge, the potential here is going to in such a way that it will create more Cooper pair or no Cooper pair or less Cooper pair. But by changing this RF field, you can also change the potential here. Okay, and this potential can help to create a extra qubit, no qubit. So this way, by with the RF also, one can actually do the same job. Okay, so this time dependent voltage of the microwave that going to shake the potential of the island, and because of this, you can see these Rabi oscillations. So this Rabi oscillation will take place depends upon which basis you are working. So for example, if your initial state is 0, that is done by Vg equal to 0, then Rabi oscillation will take place in this state. Okay. And let us say that your initial state is a plus and minus. And this is done by when the Vg equal to when Vg equal to E by Cg. Then in that situation, when you shine the photon, then Rabi oscillation will take place in this way. So either you can work in two bases. So one computational basis. This is true when the Vg equal to 0, or you can work in the hard mode basis. And this is true when the Vg equal to E by Cg. I mean, these two situations you can use. Okay. So in both the cases, you can create Rabi oscillation. And according to that, depending upon the situation now, you can use the pi pulse, or you can do a pi by 2 pulse to create different types of gates. So of course, what microwave will do, okay, it depends upon the basis. So in the computational basis or charge basis, so transition will be between 0 to 1. And in the hard mode basis, so hard mode basis means if I go back and show you the diagram, here you can see in this case. So in the hard mode gated hard mode basis, this your spin will be, or the direction of this field spin will be on this direction. Okay, so in that situation, the magnetic field in this direction, and the spin is in the plus state or minus state. Okay, so this spin is going to rotate. This spin is going to rotate about the magnetic field like this way. So this plus state is going to rotate about the magnetic field. And this is the way you can see the qubit is going to move. Okay. So that is the way one can achieve all possible types of gates by changing the voltages and working with the two computational bases. I hope it's clear. And one last part in this is called the issue in the in this platform is a charge noise. See, when I say charge noise, so it means you can see that the number of charges or Cooper pair which are produced or extra Cooper which are produced, and because of that, the energy landscape will going to change. So, for example, if I try to plot energy spectrum of a charge qubit, in two cases. Number one, let us say EJ 0, and second case when the EJ is not equal to 0. So when EJ is 0, it means total energy consists only of the charging energy. Which is of course, which is parabolic with the NG. You understand? Charging energy means 4 times EC n minus NG whole square. So this charging energy, when you plot, that is what is called E here. So when you're going to plot this charging energy, so depending upon the value of Ng, so see if Ng is 0, so when Ng is 0, then this E will be equal to what? 4 times EC into N square. So this E, when you're going to plot, so this is going to be a parabola. Like this way. So this is the case when the Ng equal to 0. But if Ng equal to, let us say, plus 1, then in that case situation, this E is going to be 4 times EC and N minus 1 whole square. This parabola will be there. So let us say this is Ng equal to 1, this is Ng equal to 2, Ng equal to 3. So in this situation, maybe I have made a big parabola. I can. So here you can see that you will get another parabola. Similarly, when Ng equal to minus 1, then you will get another parabola here. And so on, you can make it like that. And in this case, you can see that you have a different number of Cooper pairs on the island. Okay. For example, 0 means 0 extra Cooper pair, 1 means 1 extra Cooper pair, 2 means 2 extra Cooper pair. You will get this parabolic energy. Charging energy will be different. And in this case, the charge state on the island will be definitely 0, 1, minus 1, and so on. And they are completely independent. And for the case of EJ, so this is the case for the EJ 0. But now if I go for the EJ not equal to 0, so in this case, maybe I can avoid this mathematics too much. Simply I can say, I mean, in this case, Josephson junction going to couple the char states, okay, and this will going to cause the energy level splitting. Very similar, like now you can think about in solid state. Just a
Sorry,
minute.
but yeah.
Just a minute. So you can think it like in a solid state when the band gaps are how the band gaps evolve in the periodic potential. So similar kind of things going to happen here also. So so this is the how a potential is going to modify. Just a minute, I will come to the question. Let me first complete this. And so this is how this energy going to look like in this case. I mean, this is actually for the excited state, and this is for the ground state. And if I just take only one case, I mean, this gap is nothing but a EJ here, and that gap is no longer exist in the case of EJ when it's 0. And if I just look at the only one graph, so let us say again, this is the NG, and NG here is a 0.5. Okay. So half of the value, I mean, you can see here now, if you look at here, the NG 0, NG is 1. So at half value, okay, this is the graph you're going to see. And in this case, the separation, which I can call as the EJ, and this is the excited state. This is the ground state. You can call like a plus state and minus state. Now, what I'm trying to convey here is very simple. Now, even if you forget about this whole graphical part, the message which I want to give you is the following. Okay, you can see this is the 0 energy, and here it is the 0.5, and let this is the so if you change this NG, either if you go on the right side and if you go on the left side. So at NG equal to 0.5, delta E, that is the E01. This is the minimum EJ, sorry, that is the minimum. But as soon as the NG changes from the 0.5, then delta E is going to be more than the EJ. So you can see that if the NG changes, so this gap is going to change a lot. And since this NG is controlled by the VG, so what will happen? Now you see that if this gap is changing, so you are changing the gap between the two state, okay, 0 and the 1 state. So if this gap is changing all the time, okay, it is something like in the spin qubit, you can think like this way. You have a spin 0, you have a spin 1, and this is the gap you have, that is called delta E. We talk about 2 mu B into B. And this is the photons you are using to excite the frequency h cut omega. And this is going to cause Rabi oscillations. But imagine that if this gap is keep changing all the time, then it become very difficult for now for this frequency to excite this motion. And this is exactly what happens here. This gap between the two states, okay, these are keep changing if the NG is changing. So if NG is keep changing and very small change, okay, with a small change in the NG, you can see that the energy gap is changed a lot. And if energy changes a lot, then you are no longer no, in the state where you can create superposition. Now, it's very much okay if you have a very precise power supply. And keep in mind that this is the voltage supply I'm talking about here. So if this voltage supply is very precise means the change in the voltage in the range of 10 to the power minus 8 to 10 to the power minus 9, okay, that is the fluctuations or stability of the voltage, then no problem, okay. But if this power supply is not stable, then it will going to cause the change in the NG. So the one cause is the power supply instability. And even if you get a very precise power supply, even if this qubit interact with surrounding, EM waves or any static charge or static field or static field due to any charge plus or minus q, or any magnetic field, maybe because of magnetic movement of electron nucleus, if they're present, okay, this going to alter the potential island, okay. So this potential of the island will change here, and when the potential at this location changes, then this is going to alter this NG, okay. So the extra amount of charges which is going to be there, they're going to alter. So it's not only the power supply, but how these qubits interacting with the neighboring system. And this is the reason that these superconducting qubits, they are highly prone, because this NG is going to change a lot, not only because of the change in the power supply, but also if the qubit is interacting with the surrounding. And because you are in the medium, okay, having a huge amount of material around that, okay, is not a vacuum. So these qubits are not going to be very much stable. And this is the reason that because of this, the coherent times is going to reduce. Generally, it is only this much, okay? The coherent time is this much. What I mean to say that if you create a superposition, let us say you create a superposition state, so this state will survive only for, on an average, 10 to the power minus 6 seconds. After this state will destroy. And if this state is destroyed, so if you have made a gate using this state, then that gate will not going to work. You can think it's like you have a transistor. And this transistor has been used to make a gate. And because of some reason, if this transistor no longer working, or let us say destroyed because of, let us say, extra field or potential, then this gate also not going to work. And let us say in the full adder, you are using this gate, or let us say you are using NAND gate, then that full adder will not going to work. So here, this transistor is like a qubit. And these gates are the quantum gates. This is a quantum gate, and the full adder is the quantum circuit. So this qubit is what? Maybe a plus state, or a minus state, or 0 state, or 1 state. So if this qubit is gone, okay, this qubit is no longer in the state where you have left it. It is equivalent to destroying a transistor. It is equivalent to destroying a gate, means you have destroyed the quantum gate. Means the quantum circuit is no longer valid. And that quantum circuit is used for the arithmetic operation or any other task which you want to perform. So that task will not going to be performed at all. And you can see that in this situation, this system not going to work at all. So if I can't control, keep in mind, if I can't control NG, and if let us say this is keep fluctuating, let's say it become 0.49, sometime become 0.5, and then 0.51. If it keep fluctuating, okay, this will going to change the energy separation. The separation will keep changing all the time. And this will going to change the, destroy the qubit. And this is what is called the charge noise. Because this is produced because of the change in the NG. NG is a charge, okay? So because of change in the NG, this noise is created, okay? And that's why this is called a charge noise. And this is the biggest problem, okay, in the superconducting qubits. This they are highly prone, okay. So there are different type of versions, okay, they are there. But we understood one single part, okay, that is called the charge qubit. And to handle this problem, I mean, this decoherency is not a problem of only superconductor qubits. It is also a problem of the other platforms also. And for that one, if one qubit gone bad, okay, so everything will be going to be destroyed. Now, to make sure that your whole program doesn't spoil, generally we do some kind of quantum correction, which I will discuss now separately. So this quantum correction, I will tell you how it is done. Okay. But this is all about this superconducting qubit, how this charge, for example, charge qubit is produced, and how this charge qubit is actually equivalent to a spin qubit. Means we can create a block sphere, and by just using this microwaves, we can also change this state of the qubits to create different types of gates. So we understood this mathematics of the charge qubit. And today I will also take care of one more type of platform, that is called the quantum ion trap qubit, or ion trap based quantum computing. But before I jump to the next platform, if you have any doubt or question, please let me know.
Thank you. I had a couple of comments and questions. So in the case when EJ equals 0, in the graph that we have, do the overlapping graphs, the points where they intersect, do they have any significance?
Just a minute. Yeah, tell me.
Yes, in this graph on the left, since NG is a fraction and it can vary. So when going from -1 to 0, when the graphs overlap at the points of intersection, do they have any significance, any role
I
to
mean,
play?
this is not, I mean, this is the case we are explaining, but this is the case we will be working. This is the working situation.
Okay.
E is not equal to 0. This is not the working situation.
Okay, thank you. So in the next graph, in the bigger inset graph, should it not be 0.5 times EJ and minus 0.5 times EJ? In the graph on the right.
What do you mean by 0.5 time EJ?
In the graph where we discussed the
Yes,
energy
yes,
gap.
definitely. This is going to be EJ
Yeah,
by
in the
2.
graph below this, yes, in the graph below this. It should be on the y-axis, it should be 0.5 times EJ and minus 0.5 times.
Yeah, I think better to, this is
Yes,
going to be a
exactly, yes. Thank
EJ
you.
by 2. Yes, that's correct.
Yes, and
And
when
this
you
is going
say,
to be a minus EJ by 2. Yeah.
yes, and when you say that the precision power supply VG should be of the order of 10 to the minus 8 to 10 to the minus 9, are we talking of volts or micro electron volts or electron volts? What's the unit there?
No, it's volt.
Thank you. Okay. Thank you.
Yeah, okay. Thank you. So let's also then move to the second platform. And for that one, first I will like to show you some PPT. Okay, before I start PPT, maybe again I can go back to our this part. Okay, so the next in the next part, I will not do too much mathematics. Already we have done enough mathematics for this case, but this mathematics is enough to understand other systems also. So now the second platform we're going to use, that is called the ion trap based quantum computing. So see, this ion trap, actually a kind of device to trap charge particle in 3 dimensions. And they are of 2 types. So one is called Paul trap, and second is called a panning trap. So Paul trap use the RF plus DC to trap ions, and panning trap use a DC electric and DC magnetic field to trap ions, or maybe electron also. I mean, both. You can trap ions also, you can trap electrons also. So how it is done? Okay. So this is the basic definition for the Paul trap and the panning trap. So how we can do it? No, think about the situation. You have a plate, and this plate and 2 plates, and there's a plus charge and positive potential here. Now, if I create a charge here, and let this charge is a positively charged, okay, and if this charge moves upward, what will happen? This charge is going to push it back. When it goes down, then again it's going to pull upward. So you can see this charge is going to oscillate between upper and lower plate. So I am discussing this case of a penning trap. This is how it works. But let us say if the charge is moving on this direction, then it will definitely going to come out. So I can achieve trapping only in a vertical direction, but these ions can escape radially. But what if I put magnetic field? So in the magnetic field, you can see that if charge particle is moving in this direction, then it is going to actually circulate about the magnetic field. So here, this charge particle is also going to circulate. So this particle is going up and down also, and this particle also trapped in a circle. So this is a way you can see that we can create a three-dimensional trapping. So this is the basic principle how this panning trap works. Okay. The same mechanism can be done by Paul trap. Okay. So in the Paul trap, what happens that instead of using the DC electric field or DC magnetic field, what we use RF field. So RF field is like that way that imagine that with the RF field, I can create this kind of potential well. And imagine that if this charge particle is sitting here, or maybe how I can, with pencil, it is always difficult to draw. In 3D, it looks very simple. Okay, think about a potential like this in this direction, that is called the Z direction. But along this direction, this potential is having this nature. So it means along Z direction, this particle going to oscillate to and fro, but this can actually going to roll down. Okay, roll down along the X and Y direction. So let us say potential dip is only along the Z direction, but other direction is open, then this is going to roll down in the X and Y direction. So what I can do, so when the particle is getting rolled down along the X and Y direction, so what I can do, I can just rotate this potential. Okay. So this potential is going to rotate it. For example, in the one cycle is along Z direction. In the next cycle, it is now along the X axis. Okay. Then this is going to rotate all the time. And you can see that this way, this particle will always find itself in the trap. Okay. I mean, here, even if you don't understand fully how the trap works, it's still fine for me. Okay. Because here we are not we are not too much this requirement is not too stringent to understand the quantum computing. But just keep in mind that these two types of trap, Paul trap and penning trap, they are two technologies used to trap the charge particles. Okay. And once these charge particles are trapped, okay, then we can use these charge particles to do the quantum computing. And my focus will be to let you understand that how this quantum computing is done with the trapping. Okay. So for this one, maybe I can okay, just I have one animation which will actually little bit help you to understand. In reality, this is how a penning trap look like. So we have a three types of cylinder. So this is the one and another one, and we just give them a name. So the first one is called end cap. The second one is called ring electrode, and third one is called again end cap. Now, if I put some potential, positive potential, zero potential, and positive potential, then you can see that because of this potential on the electrodes, okay, you're going to have a potential valley or potential well. And of course, there are some mathematics which I can ignore here. So now imagine if I create a charge particle here, and this potential height is let's say this much. This is a potential height. So if I create a charge particle, the blue one, and if the kinetic energy of charge particle is less than the potential height, then this particle will not able to escape. So what will happen that when the particle is going on the left, this potential going to push in the right. When the particle goes on the right, this is going to push in the left. And this is the way the particle will keep oscillating. And you can see on the bottom picture also how the particle is keep oscillating. But of course, this particle can escape radially outward. And for that one, what we do, we apply a magnetic field. Look at here. This magnetic field we apply. And because this magnetic field, this particle is going to rotate in a circle. And this is the way you can see that we can create a three-dimensional trapping. Is this clear? A basic understanding of the ion trap. Any question up till here?
Sir, the voltage you provide, is it continuous or it's a step voltage? Like
It's
plus to zero.
no, it is a continuous.
Okay.
The voltage remains fixed all the time. Okay. And when this particle is oscillating, you can see that they oscillate in this direction with the frequency that is called the axial frequency. And when they rotate in the circle, that is the frequency that is called the cyclotron frequency. So these two frequency I will discuss later on when we need this, but this is how the particle is keep oscillating. And I mean, the actual motion is quite complicated, but not required. Fine, up till here. Now coming to the quantum computing part now. So once these ions are trapped, so you can trap different types of ion. So for example, the most suitable ion for the quantum computing is a calcium. So you can see that if we look at the calcium ion, which I mentioned that is the more suitable ion. So here in the calcium ion, how are we going to create a qubit? Let's look at. So calcium is atomic number 20. So configuration become 1s2, 2s2, and 2p6, then 3s2, 3p6, and 4s2. And to trap in the panning trap or the Paul trap, what we do, we're going to make calcium 1 plus. So 1 plus means everything is same, and 3p6, and you take one electron out of the S. Okay. Now you have now only one electron in the S state. So this is going to have a spin half, and as a result, the this multiplicity is going to become 2. And since L is 0, so J is going to become half. Then the state become what? 2s1 Lj, correct? So the state becomes 2s half, correct? So the ground state of the calcium ion is the following. Look at here. So this is the 4 2s half. This is the ground state. Now, the first excited state. If you look at, means in that situation, what happened that this electron from the 4s, okay, they can go to the 3d1 and also to 3p1. There are two possible excited states you can see. So if they go here, then here you can see this
Sugam, you mean 4p? Because 3p is occupied, no?
Yeah, sorry. Yeah, 4p. And
No, 3D may, but
3D,
4p.
yes, 3D and 4p.
but
Yes,
4p.
that's correct, exactly.
Right,
Sorry,
right.
yeah. So these two states are possible. And in this state, the spin is there and spin is half and L is 2. So there are two states are possible. So one is called 3, 2D. It is going to be a L2, so 5/2, correct? And one state will be a 3, 2, D, 3/2. So there are two states possible. And here also, two states are possible. So one is called 4, 2, P 3/2 and 4, 2, P half. Okay. So you do little bit spectroscopy, you will find the energy levels also. And what you find here is that these two D levels, okay, they lie here. That is the 3, 2D lower. Since this is the less than half filled state, so according to Hund's rule, lower J will have a lower energy. And this is the 3, 2, D 5/2. Higher J will have high energy. And this is the 4p, of course, is a higher state. So this state lies here somewhere. There are two more states. So that is the 4, 2, P half is again less than half filled state. So you can see this is the electronic configuration and different configuration and the different states in this situation. And now these states, this state, the separation, very important for us, that is a 397 nanometer. And this transition state, this one, is actually a 393 nanometer. And one of them, this one, is correspond to 729 nanometer. Now see, for the transitions, you know that the delta L, okay, plus minus 1. No, if you have multiple state, then this is 0 also. And delta J is going to be 0 and plus minus 1 also. So you can see that this is for the electric dipole transition or the even transition. So certainly you can see that these two states, no, these D states, because here L is 2 and here L is 0. So this transition from D to S is not allowed under the electric dipole transitions. It means these states, they are a metastable state. Both are metastable state, but the transition can take place from the P to S, okay? Because here L is 1 and here L is 0. So the selection rule is fulfilled for the electric dipole transition. So these are the normal states. Clear to everybody? So now I can take you back in this diagram here. Come back. This is what I have shown here. No, maybe we can save some time now instead of drawing everything. So these are the electronic configuration for the calcium, and these are the electronic states. And what we can do, we can actually use these metastable state. No, I can mark as a 0 and 1. Okay. So this ground state, when the calcium 1 plus ion is in the ground state, then that state I can mark as a bit 0, a 0 quantum state. And when this is in the d5/2, then I can call this as the 1 state. So I can use this 4s half and d5/t, these two states as the two states corresponding to the equivalent to our spin state 0 and the 1. So you can see in this situation, we had a spin up and spin down. And in this case, it is the ground state of the calcium and the first excited state of the calcium. So these two can be used as the two states, and these two states can be act like a qubits. Is this clear to everybody? All right. Now, how to then excite these ions is very simple. I can simply shine a laser. Okay. To excite these motions. I can use these normal states also. And I will tell you how these normal states are going to be play an important role, because they are here going to use for the read back. But at least the first task is clear, that we can use these quantum states 0 and 1 as the qubit state.
Sugam, can I
Yes.
ask a question? Yeah. So here, the line, I mean, the levels you have chosen, they are not dipole allowed, right?
No, they're not dipole allowed. They can be allowed through the higher modes of transition, but not through the electric dipole.
Yeah, but so when you shine, the dominant transition is dipole, no? So how do you excite this from 0 to 1? You just said, no, we shine the light and make the transition from 0 to 1.
Uh, just 1 minute.
Perhaps they go via the P stage.
This is go via through the BP state actually. That's my mistake. Actually, we excite first to the P state, and
Right,
from
right.
there they come to the 1 state.
So they de-excite to the D, right?
Exactly, D side to D,
Yeah,
not
right.
directly to the, not directly through the shining photon to the D state. My
Right.
mistake, please. Just. So not only calcium, but different other ions can be used. For example, beryllium also can be used. Magnesium also can be used. No, barium also can be used. No, there are different types of no, candidates are available. Okay, which can be used no, to use them as the qubit. Calcium is more popular because these lines. Okay, 393, 397. Okay. The laser for these lines are easily available in the markets. And this is the reason that people mostly know using this calcium in many laboratories. So this is the electronic quantum states. And now we understand that these can be used as the qubits. Now let's try to understand how to then make a quantum computer out of this. So first of all, what we do, we use, so this is the Paul trap. And in this Paul trap, this red one is the ions. Each is a calcium 1 plus. So each dot here is a calcium 1 plus. And actually what happened here in the Paul trap, generally we have a positive potential here and positive potential here on these two electrodes. And on this one is the RF field. And here also RF. And here also RF. Okay. So what happened that these ions, okay, so as I told you that these two act like a plate, a positive plate and positive plate. So when the ion is here, it will push on this side. When the ion is here, it will push on this side. So you can see that there are large number of ions here, and they all are positively charged because they are calcium ions. So you can see in this picture how they are oscillating. Okay. So each dot here is actual picture taken by the Michel, no, from the Los Alamos. So here each dot, the light spot, is actually coming from a one trapped calcium ion. So when these calcium ions de-excite from the normal state, so they're going to emit light, and this light then you can collect on the CCD, okay, and you can see them. So I'm in that sense a very beautiful picture that you're seeing each atom individually, and you can see that these atoms are oscillating, okay, in this potential well. So there are maybe I can, in fact, I can tell you there are two different types of oscillations can take place. So one oscillation is of course this one, and other of course this also. Okay, so these two types of modes can be produced now when the ions are trapped inside. But I'm coming back to here again. So there are two types of motion. Okay, but let's consider only one this motion. Okay, this is called common mode. So these ions are oscillating, so they are like a quantum harmonic oscillator. So now we have a so let me take you back on the notepad. So see what happened now. So there are electronic states. Plus there are vibrational states. So when these ions, they each are calcium ions, and when they are oscillating, so they are like a couple oscillator. So they're going to oscillate and they're going to produce a potential, and this potential is then going to be a like this. So when these ions are oscillating, so this energy can be in this state, or in this state, or in this state, or in this state. But since they are very heavy ions, okay, so if you want to really bring them to the ground state, you have to cool them, okay, to 10 to the power minus 6 Kelvin temperature nearly. So around less than this temperature, you have to cool down if you really want to populate them to the ground state. So here, now onward, I'm going to use the two levels, two systems. So one is the N. So this N is the vibrational quantum number, quantum or quantum state. And then these electronics level like D 5/2 and S 1/2. So these levels I can use as a Q. Okay. So when you have a one calcium ion, okay, so one calcium ion, so corresponding the Q I can call as the Q1. You have a second calcium ion, corresponding I can call as the Q2. Then you have a third calcium ion, and corresponding the state I can call as the Q3. So I'm going to use these Q1, Q2, Q3 as a logic qubits. I'm going to use them as the logic qubits. And these n states, okay, vibrational states, so they are correspond to the common mode vibrational states. And the value, of course, of this n can be 0, 1, 2, 3, and so on. So, for example, if I say, no, if I say that n equal to 0, it means the all these oscillators, they are in the ground state. So they are here, means no phonons. These vibrations correspond to energy, and those energies are called quantized energy called phonons. So N0 means no phonons. But when n is equal to 1, then I will call one phonon. When n equal to 2, then I will call two phonons. So technically, this n is representing the number of phonon in the common mode. So when these charged particles are oscillating, so if they are in the ground state, then of course there is no phonon involved there, because they no longer I can say having any vibrations in this state. But they have energy, and this energy of course is equal to h cut omega by 2. That is called the 0-point energy. But when they go into the first quantum state, then I will call they have only one phonon, so they are vibrating now. Okay, and energy is 3 by 2 h cut omega. And this transition, which is correspond to h cut omega, this correspond to the energy of the phonon. So when you supply one phonon, so this energy will go to this level. So one phonon, then here means two phonons, three phonons. So these numbers are representing the number of phonons. So n is actually representing the number of phonons in the common mode. So I hope this nomenclature is clear to everybody. So for example, if I write these are going to be a tensor product, so I can say Q1, Q2, Q3, and so on. And if I say, let us say 0, so I can say this is a state. This is a state in which ions are not vibrating, or I can like say like this way, n equal to 0. Because there are no phonons. Because there are no phonons. But when you have a torque state like 1, 2, 3 like this, and n equal to 1, so this is a state, okay, contain one phonon. And this in this state, the atoms are or ions are vibrating, and all the ions are vibrating. So all the ions are going in one direction or in this direction. So this is the common mode oscillation. And in the ion trap computing, this common mode is used, okay, as a bus. that couples different ion together. So all the ions, they all going in the same direction, or they all going in this direction. This is called the common mode. Clear? I hope so up till now. So we can use two types of states here. So one is the electronic state and one is the vibrational state. Electronic states is correspond to the electron position in the atom, and vibrational states is correspond to the vibration of the ion itself. All right, clear to everybody? So how we do the quantum computing? So in the Paul trap, you have different types of many ions. So each is calcium ion. And they are each having a different quantum state, Q1, Q2, and so on. But collectively, they have a one state called N. Okay. So this N is not individual, remember. This Q1, Q2 is individual, but N is not individual. But when these ions are oscillating, then I can, what I can do, I can cool down the whole system down. And let us now see that I'm going to make a vibrational levels, and then I'm going to make two levels only I'm going to show here. So this is the N equal to 0, and this is the N equal to 1. And let us think about the two calcium ions only, So only two calcium ion I'm talking about. So those the two calcium ions, they are also, let us say, in the ground state. So when I say ground state means they are in the 2s half state. So this is the ground state. So maybe how you can show the ground state, let us say I can use some only 0. So there are two ions and they are in the ground state, and they are also in the vibrational ground state. So this kind of nomenclature I can use, that both the calcium ions, they are in the electronic ground state, and they are also in the vibrational ground state. Fine. So this they are some nomenclature I'm using. Now what I'm going to do here. So let us say that for the qubit transitions, so let us say for the qubit transition, the frequency required is omega naught. And for let us say common or vibrational motion, or for let us say N0 to N1 transition, the frequency required is omega 1. Now see something called a coupled motion or coupled excitation. It means if I shine omega naught plus omega 1 and omega naught minus omega 1, since you can think it like a large number of pendulum together, okay? So their motions are coupled together. So if they are oscillating with the frequency, let us say omega, let us say omega dash and omega double dash. Then even if I shine frequency called omega and omega dash and omega dash, so even this oscillator is going to oscillate with the frequency this one, and this one also, and this one also. It is clear? So if they are coupled oscillator, so you're going to have oscillation at this frequency also, at this frequency also, and of course these are the definitely going to excite them. So here, this is the frequency required for the qubit transition. This frequency required for the vibration transitions. Okay. And if I shine, let us say this frequency, this is called the blue band or blue sideband. And this is called the red sideband. So even this excitation can take place at the blue sideband and the red sideband as well. So how I can denote them? Let us say on this side is the frequency. So here I can say that this is correspond to omega naught, and this is the omega naught plus omega 1, and here let us say omega naught minus omega 1. So transition can take place at here also, but if the transition takes place only at this frequency, so in this case it means you are shining photons, okay, which going to only excite the qubits only, okay. I mean, so it's going to make transition from 0 to 1 through the P actually from the meta, not through the directly metastable, but through the normal state. So that transition, okay, is going to excite, okay. So if you're going to shine, let us say omega naught, then it is going to cause only, let us say 0 to 1 transition. So here you can see that this is going to cause 0, and let us say if the atom is already in the vibrational state n, so it will remain there, and this is goes to 1 to n. I mean, technically this is going from 2s half to 2d 5/2, but no change in the vibrational level because you are shining photon only with the frequency this much. But if you shine this frequency, then this will cause both, because omega naught will be used for the transition to 1, and this omega 1 will use to make a transition n to n plus 1. I mean, so in this case, this is the situation you're going to have. So in this case, both the atoms will excite, so they goes to the n equal to 1 level. And maybe I can also show with the dark color. So they are also in the D state also. Okay, so in this case, this S2 D state changes, or N2 N plus 1 also changes. It is clear, this concept to everybody? In the blue sideband, what happens? Or any question?
So these are two lasers, like omega 1 and omega.
Exactly, there are two lasers, yes.
Two lasers. Okay.
And if you shine, let us say omega naught minus omega 1, okay, then in that case, you can see the frequency is less. Okay, so this is a very interesting situation because it's a red sideband. So you can see that the frequency is not is less than omega naught. Let me, this is called the omega dash. So omega dash is less than omega naught. So this cannot cause the transition called S to D. And this omega dash is too high than the omega 1. So even this cannot cause this transition because it's too high. Okay. because I will tell you that the frequency which are vibrational frequencies are very small in the megahertz and in the gigahertz, and whereas when you talk about transition frequency, they are in the now IR radiations. So this is too less enough frequencies. So this cannot cause this transition. So what happened that in this situation, let us say if the ion is already in the n equal to 1 state, and from there, if it make a transition to the ground, okay, so this omega 1 amount of energy is there, correct, which is released not in form of photons. So you can simply think that this energy is going to utilize also in omega naught, and that going to make now frequency exactly omega naught minus omega 1 plus omega 1, actually omega naught in the layman language. But never think that some photons are produced and they're adding. No, it's an internal mechanism is happening there. Okay, so this photons are this excess energy is used in this case, and the energy is equivalent to omega naught, and that can cause the transition to S to D. So here what happened that you are, let us say, in the state called 0 and n. So you can see that this is going to become n minus 1. So it is going from n1 to n0, and then this is also going to go 0 to 1. So these two things are very important to understand how the quantum computing works. Okay, so in the blue sideband, this is the mechanism happens. In the red sideband, this is the happens mechanism. So in the blue sideband, very simple. You have a frequency higher than that, and this frequency will be used to make a both transition S to D and also from N0 to N1. Okay, in the blue sideband. But in the red sideband, it is going to make N1 to N0, and then S to D will take place. It means S to D will take place only and only if ions or this vibration is already in the n equal to 1 state. So please let's take a break here for 1 minute and try to little bit digest this part, because this is something is important to understand the ion trap quantum computing. I'm not going to the mathematics. I'm just trying to explain the concept only through the basic understanding. Now you already also know about the pi pulse. So when this Rabi oscillation take place, so pi pulse is correspond to this location, correct? So here you can see that 0 to 1 transition takes place. But then there is a position, this is a pi, and this position is called pi by 2. And in pi by 2, what you're going to have? You're going to have a superposition of 1 and 2. So look at, let me draw one more diagram. So let's try to again think about quantum, this harmonic oscillator, and both the ions are in the ground state of the electronic and ground state of the vibrational level. So here I'm going to use symbol, let us say when I say black, okay, so black mean ground state, means S state, means 0 state, means ground state. And let us say I use the red. So red I use, then it means a D state, means state 1 or excited state. And of course, when I say n equal to 0, this is the vibrational ground state, and n equal to 1, this is the vibrational excited state. So look at here. If I shine on this a laser of frequency omega naught plus omega 1. Now you take a laser, a single laser whose frequency equal to this much. Then what it will cause? It will going to excite both. So you can see that in this situation, so this state is going to so let us say that you shine laser of omega naught plus omega 1 on this is the 1 and this is 2 on the first calcium ion. You see, I mean, if you look at the picture here, you can see that these calcium ions, okay? So they are one calcium ion here. Let us say this is the 1, and this is the calcium 2, and this is the calcium number 3. So I'm going to shine photon on this one, okay? Not on the second one. And this can be done because the separation between these calcium ions in the micrometer. And I can use a laser, okay? Very fine laser, okay? Fine focus laser, which can actually hit only the first calcium ion, not the second one. So in this situation, you can see what's going to happen. If I shine on the first one, I mean, technically this photon is going to hit only on the first one. It means this first ion is going to go from this is the first and this is second. So this first position will change to 1. The second still remain the 0. It is clear. And this omega 1 is also going to excite this into the n equal to 1 state. But remember, both the ions, they are linked together. If one ion oscillate and goes to n equal to 1 state, the second ion also going to n equal to 1 state, because both are linked together, not both are couple oscillator. So if the first ion excite or start vibrating, the second ion also going to start vibrating. It means both the ions will be in equal to n equal to 1 state. So here you can see that I can say the ion number 2. The ion number 2 still remain in the S state, but now it is goes into n equal to 1 state. The first ion, now it will be in the D state, but this also will be in the n equal to 1 state. So this is the quantum state. You can see we have. This is true when you're going to shine a blue sideband frequency. Is this clear? And now I can tell you that how to create a gates. So I can give you example. Let's try to create a C0 gate in the ion trap. So if I want to create a C0 gate in the ion trap, what I can do, again, the same mechanism. I will take a potential of the harmonic oscillator, and I can show the 2 levels. Okay, so this is the n equal to 0, and this is n equal to 1. And I can say 2 ions, both are in the ground state of the electronic ground state, and also in the vibrational ground state. Then what I will do, I'm going to shine in the first step. I'm going to shine photon on the first ion. But let us say I shine blue sideband. Blue sideband. But let us say pi by 2 pulse on first ion. Now you know that when you shine pi by 2 pulse, so this ion, okay, but in the blue sideband, okay, means you are shining frequency omega naught plus omega 1. So this omega naught will going to cause a transition from 0 to 1. But because this is a pi by 2 pulse, this transition not complete. So this is going to put into the superposition state. This will not take place, only this will take place because of the pi by 2 pulse. And this omega 1, okay, this is going to now go for the vibrational transitions. So see what going to happen here. I can draw a potential well. After this pulse, now I will draw two, I mean, either this possibility or another possibility will exist like this. Because these ions will be in the S and D state both together. So I can say that this ion, if this is 0 state, then I can show like this is like a black. If this goes into the 1 state, then I can show it like a it is show like a red. But if this is a red position comes, then in that situation, omega 1 also going to add up, and then particle will go into the vibrational higher state. And second, of course, ion will be, you are not shining anything, so it always remain in this state. And here also it will remain in the same state. So you can see that this is the situation you're going to achieve. What is this situation says? Here, look at what this is the 0, 0. And ion in the n equal to 0 state. Or maybe I can just simply write like a 0. And plus, what is here? Here you have a 1, 0 and 1. Okay. So this is the quantum state you got. Can you think if this state is a not a Bell state? This is not an entangled state. I want to create an entangled state. Then what I will do? There's the next step here. In the next step, what I will do, I am going to shine a red sideband. But pi pulse on second ion. So I'm going to shine on the second ion. This is 1 and 2. I will shine on second ion. Okay. So I will draw these two potential. Potential is only 1, but in a superposition. Now see, understand here. When you shine photon on the second ion, and you are shining the pi pulse. Now pi pulse is going to cause 0 to go to 1, correct? But look at this red sideband. Red sideband means the frequency is omega naught minus omega 1. Now see, this frequency is less than omega naught, so this cannot cause this transition. And this is too high than the omega 1. This cannot cause the transition from N0 to N1. So what will happen? You can see this red sideband transition will take place only if the particle is already in the N equal to 1 state. Because from there, particle can go from n equal to 1 state to n equal to 0 state. And this energy, which is omega 1, this is, I can say in the layman language, will add up here and going to make omega naught. And this omega naught then cause particle to go from 0 to 1. So in principle, you can see that there are two levels. So nothing going to happen here, because in this situation, the particle is already in the ground state. So this red sideband not going to alter this state. The red sideband is going to alter this second state, this one, because here the particle is in n equal to 1 state, and from there it will fall back. So this particle is going to fall back to the ground state. But remember, when the second particle is going to come down to the ground state, okay, then the first particle also going to come down the ground state, because these are vibrational levels. Both the particles will be in the ground state of the vibrational level. But at the same time, when it's come down, okay, you can see that. So you can see that the second particle also come down. What happened to first particle? Look at the first particle actually now got energy omega naught, and in this case, this transition will take place. And as a result, the first particle also will be in the D state. And here the state become what? Look at here. Both are in the 0 electronic state and 0 ground vibrational state, and both are in the excited electronic state and ground state. That is a 1 by root 2. And this is actually a 1 by root 2, 0, 0, and 1, 1, and 0. Look at, this is the Bell state or entangled state. So you can see that this is the way we can create an entangled state here. And this is also a C0 gate. Why I'm saying C0 gate? Because in the C0 gate, what happens? You can see if this is the qubit 1, qubit 2, and if this is the 0 and 0, then here you can see that this is C out, 1 and 2 out. So this is going to be 0 and 0. This is 0, 1, then 0, 1. This is 1, 0, then this is become 1, 1. This is 1, 1. This is going to become 1, 0. So the target, this is a target, and this is the control bit. So you can see that here the one is going to act like a control bit, and second is going to act like a target bit. So it is a superposition. So I think I should avoid not targeting the single ions, okay, in this way, because this is superposition state. But what I'm trying to say here, look at when this ion number 1 is in n equal to 1 state. Okay, so technically this is the control. Okay, the control is the vibrational level. So what is going to cause when this is n equal to 1, okay, then only the transition will take place. When this is in n equal to 0, nothing will happen. This is what is happening here. So when n equal to 1, then 0 is going to become 1 and 1 is going to become 0. So here you can see when this target qubit controls is in the n equal to 1 state, then only this transition takes place. The spin transition will take place, else it will not take place. So this is also acting like a control C0 gate. But this is how you can see we can create an entangled state. So that was the basic idea how this in terms of ions, how these ions qubits are working. And quickly I can give you some more idea. A second type of ion trap. So this is the trap I am working on, that is called the panning trap. So at IUAC we are developing this trap, and in this trap, as I mentioned that how these potential on the electrodes, they're going to cause this potential well, and then you can create a particle, and this particle will be trapped with a frequency this, and magnetic field going to cause the rotation in the radial plane, and this is how you can create a 3D trapping. Now, for the quantum computing, in the case of the panning trap, these cylindrical traps will not work. So what our plan at IUAC is that we want to trap electrons, and with the electrons, not ions. So at the work we are doing at IUAC is not exactly, we're not using the ions, but we're going to trap electrons. And I'm going to use the electron spin as a qubit. So here we're going to use electron, not calcium ions. So what I shown you previously, that is the mechanism done by different labs or many companies. For example, you can think about IonQ company. So IonQ company using these Paul trap and the calcium ions and the rubidium ions to trap the ions and to do the quantum computing. But what we are planning at IUAC is the panning trap, to trap electrons and use electron spin, okay, as a qubit to do all the calculations. Okay, so in this case, what we're doing, we have a two plates. So let us say plate number 1 and plate number 2. And you can see if I want to trap electrons, okay, or let us say, then what I will do, I will put some potential, or if I want to trap some positive particle, accordingly, I can, so for example, in the case of electrons, I will put negative potential here and positive on this one. So positive here, negative here. So you can see here the electric field profile. So just focus here at this point. So at this point, the electric field lines are reversed. And this is the point where the potential is going to become minimum. So if I trap electron here, so this electron not going to move down, because if it's going to move down, this negative potential going to push up. And if this goes up, the electric field direction will going to pull it down. Okay, so this particle is going to oscillate here up and down. So this particle is going to oscillate. So this is the way you can see that we can create a horizontal up and down vertical oscillations, and then I can apply magnetic field, and this particle is going to rotate in this direction. So here also you can see that I can create a 3D trapping. So and so on each, for example, on each trap, I can trap one electron. So each trap here is going to act like a qubit. Okay, so you can see I can make a large number of qubits on the surface. So we can manufacture these small rings, and they are very small in size. You can see only 100 micrometers. So we can fabricate such large number of such traps, and we can trap electrons at certain height. So these electrons will be just, you can see here, 30 micrometer above the surface. And they are going to act like a qubit. And this is another picture. You can see this is the ring number 2, ring number 1, and this is the point where the electric field profile changes. And this is the place where the electron is going to trap. So And you can see this is a 3D picture and how this electron, this is the electron, and this is actually oscillating up and down and also rotating in the circle. So this is a simulation which we did actually to see how the particles are oscillating. Okay, so they oscillate in the up and down, also in the circle. So when they oscillate up and down, the frequency is omega z. And that frequency is actually a 4.43. So this omega z is actually a nearly 4.43 gigahertz. And when they rotate in the circle, that frequency is called the omega c. And that omega c actually equal to 56 gigahertz at let us say 2 Tesla. If you have only 1 Tesla, that frequency is going to be a 2 pi time only a 28 gigahertz. It is clear to everybody what I'm trying to convey? Or any question you want to ask up till here?
What's the possibility of trapping a nucleus, for example, in
Yes,
this
you can.
trap?
Yes, it can
Would
be.
the magnetic field required be very high compared to this?
Yes, exactly. One can trap protons. Yes. You can trap both. I mean, for example, you can trap calcium ions also. No, it's a very heavy ions. Okay. So all sorts of ions you can trap, whichever now comes in your mind. So you can trap positive ions, you can trap negative ions also. But only thing that in the case of negative ion, only you have to change the polarity. Okay.
Yes.
For example, in the case of electrons, I am putting here negative and positive. In the case of ions, I will put positive here and negative here. But you can trap all types of ions, but only thing that the magnetic field required is very high. Okay. So for example, if you want to trap, let us say uranium, okay, 91 plus, then the magnetic field should be in the 6 Tesla region. Okay. Then 1 Tesla field will not be enough to trap.
Yeah. And then they can be used in the linear accelerator that the IUAC houses.
I mean, so if you want to use for the acceleration, then we have a different types of source, ion source. This source specifically used for the producing single ions, okay, to do a precise experiments.
Okay.
So if you in the accelerator, we need plenty of ions, and for that one, different types of source used.
Oh.
Now see, here how we are planning to do the quantum computing. So logical qubits, we're going to use the spin. And already for the spin, already we have done too much study. Okay, so here you can see this spin states. Now this if you have 1 Tesla magnetic field, energy is this much, that gap. Okay, and this correspond to 28 gigahertz. And corresponding temperature is 1.3 Tesla. But if I apply, let us say 6 Tesla magnetic field, then of course the gap will increase. This becomes 6.9 this much, and the frequency become 168 gigahertz, and temperature corresponding into 8 kilo Kelvin. So when I say temperature means let us say if I am working at 1.3 Kelvin, then you have to cool down the system temperature below 1 Kelvin. Otherwise, the temperature from the environment, okay, that going to cause this spin flip, correct? So this up spin and down spin, then I can use either 0 and the 1. And these ions in the trap, you can see they are oscillating. It is same like a calcium ions. They are oscillating. So I have a large number of electrons in the trap. So you can see that here. So large number of electrons. So they are coupled together, no? So when they're coupled together, so their vibrational motion is also coupled. Okay. So I can think about a vibrational motion. the way I given you the idea in the calcium ions. So same logic I can use. And if I want to create let us say superposition state, so same way I can apply a pi by 2 pulse, means I can just shine 28 gigahertz photons, and they can cause these transitions. But at this location, so at this location, when you are, then you are actually producing the superposition state. So this is the, let us say, state number 1, this is state number 0, but here, this is the point on the Bloch sphere plus. So this way I can create a superposition. If I shine, let us say, a pi pulse, then I can create X gate. If I shine pi by 2 pulse, then I can create Hadamard gate. If I give some phase of the potential on the EM wave, I can go for the S gate and the T gate also. And these single qubit gates like Hadamard and S gate and T gate and then C naught gate also, if I use them together, then I can make a universal gate. I mean, any kind of algorithm I can construct with the help of a single qubit gate and the C naught gate. Clear up till here? So this is some kind of repetition only. Now, how to do the computation? So here, for the computation, I'm going to use the vibrational motion. So electron axial energy, if I calculate, so same like a calcium plus ions. So you can see this is the energy. And if I keep some 10 voltage, then this frequency is this much, 4 gigahertz, I told you already. And so the temperature, so if I have different levels, if I go for the temperature, so temperature corresponding to this one is a 211 millikelvin. And this is very small. It means that if I want to really cool down the electrons to the vibrational ground state, I need to cool down the system below 100 millikelvin. So for example, I have done the calculation where I can see that if I cool the system to 100 millikelvin, then the probability that the electrons will be in the vibrational ground state is around 90%. But of course, if I go to around 10 millikelvin, then this will be going to be a 99% nearly. So that requires, this is the requirement where you can see we need to cool down the system to a very low temperature. So you can see there are two type of states here. So one is the spin up and spin down state. This one. This is equivalent to a S and D state. And then this N is the vibrational levels. And this omega naught, if you look at carefully, so this omega naught is actually 28 gigahertz at 1 Tesla magnetic field. So if I shine photon of 28 gigahertz, then this is going to cause the spin flip. And 4 gigahertz is the axial frequency. That going to change N to N plus 1. Now again, the same logic. If I go for the blue sideband, means you shining omega 1 plus omega naught, means 32 gigahertz. Then out of this, 28 gigahertz will be used to flip the spin, and 4 gigahertz will go from N to N plus 1. So this is what you can see here. The spin is flipped and N go from N1 to N plus. But look at when you go for the red sideband, means you are now 23 gigahertz. Now 23 gigahertz is less than 28 gigahertz. So this cannot cause the spin flip. And this is too high than the 4 gigahertz. So this is even cannot cause the N plus to N plus 1 transition. But this is possible if the electron is already in the higher state. And from there, if it is come to the lower state, lower vibration state, then this is going to produce phonons of 4 gigahertz. And that 4 gigahertz, you can think like adding up in the 23 and 0.6, making 28, and that 28 will cause the spin flip. So you can see here, this is the red sideband. So n is goes to n minus 1, and that caused the spin flip. So exactly same logic we are using here also. And you can see how we are going to do methodology. So initially, we're going to initialize electron in the spin ground state. This arrow is showing the spin ground state. And when the arrow flip, then I will call it the spin up state. And this 0 and 1, they are the vibrational ground and the excited state. So I'm going to initialize the system in the ground state. And how we can do it? How I can ensure that the particles are in the spin ground state and the vibrational ground state? Anybody will tell me how I can ensure? Hmm? See, you tell me, if let us say, if you want to go from spin up to spin down, okay, the energy is correspond to 28 gigahertz, and the temperature is how much? 1 Tesla, no? Now you can think that if I cool down to 100 millikelvin, then this temperature is too less compared to 1 Tesla. Energy is too less. Now think about other case. If I have 2 Tesla, sorry, uh, what I'm saying, if I have, let us say, 1 Kelvin, okay. So if temperature is 1 Kelvin, then in that situation, you can see that if I put a temperature 2 Kelvin, then the energy from the environment is too high. It will going to cause the spin flip. The spin will go up and down, up and down, up and down. But let us say if the temperature become 100 millikelvin, then the energy from the environment is less. So even if the electron is in the higher quantum state, after some time it will come to the ground state. So it means temperature plays a role here. So if I cool down to 10 millikelvin, 100 millikelvin, then after some time, electron already going to be in the spin ground state. And the same way is for the vibrational level also. You can see here in this diagram, I told you, if you go to the 110 millikelvin, then the 99% chance that the particle will be in the n equal to 0 state. So temperature is the criteria here. So if I cool down the system to, let us say, 10 millikelvin, then after a few microsecond, you are almost sure that the particle will be in the ground state. You can check also later on. You can do a pi pulse transition and you can check whether they are in the ground state or not. So if you want to check if they are ground state or not, you can just shine a pi pulse and then you can, if they excite, then they are in the ground state. And again, you can bring them down by again another pi pulse. So what you do again here, so you have a two trap. In two traps, you have a 2 electrons, and then what you do? Shine blue sideband at pi by 2. So if you shine blue sideband in pi by 2 pulse, then it will going to put electron number 1 in the superposition. And if this electron number 1 excites, then if it is a spin get flips, let us say if the spin flips, then it will also go into the higher vibrational state. If the electron number 1 goes into the vibrational state, then electron number 2 automatically also goes into the higher vibrational state. So both electrons will be in the higher vibration level. But the spin of the second electron is still remain the same because you're shining the photon only on the first electron. After this, and this is the quantum state, you can see this is a superposition state, but not a entangled state. And then what you do, you shine the red sideband photon on the second electron, but pi pulse. And this pi pulse is going to act only. So the electron number 2 is excited only if electron 1 was excited. And if electron number 2 is already n equal to 1 state, and from there, if you come down to the ground state, then the remaining that energy 4 gigahertz that will be used to add up in 24 gigahertz and make 28 gigahertz that will use to flip the spin. And this way you can see the spin of the electron number 2 also flips. Okay. And this is how you can get the Bell state, nothing but the C0 gate operation. So you can see that this is how we can also now planning to achieve this now gate operation with the electrons. But the challenging task here is that trapping electrons now in the panning trap. This not has been yet done not anywhere. So this is a major task to trap a single electron in the panning trap. Once it's done, then I hope the second other parts will not going to be too much difficult. So
how
that's
many ions does a panning trap actually trap? Or if one ion is not trapped here?
repeat again.
You just said that a single ion is not being trapped in a
Not
panning.
single, not I'm saying, I'm talking about the single electron.
Oh, okay.
Ions has
Yeah.
been trapped and single ions has been trapped various locations. Okay.
Yeah.
But single electrons not has been yet trapped. Okay.
Oh.
In the planar panning traps.
Is that due to their light mass and
No, actually, because of the anharmonicity, which is actually part of this kind of trap. So if I am working, let us say, in this kind of trap, it is possible to trap a single electron because this is creates a very harmonic potential. But when I am working in this kind of trap, planar trap, the potential is no, see, potential here and here,
Yeah,
which is different shape, is anharmonic.
true.
And this anharmonicity actually causes the problem in trapping the single particles. Okay. And we are trying to work on this. And we are trying to, actually already we have done this part. We have created a perfect harmonic potential. And now we are in process of now doing manufacturing of this trap. And once this is done, then I hope that it will be not difficult. I think in soon we will be able to now achieve
Good.
this step.
Good.
So how many qubits are you planning on this plane?
Actually, at the moment, we are planning 7 qubits.
Okay.
Only.
So calcium, when you mentioned, it could be selectively, laser can be shown
exactly.
selectively to a particular
Yes.
calcium
Yes,
ion.
exactly.
But
Yes.
here also, is it very simple to selectively excite one electron?
No. Because here you can see we are working in the IR region, correct?
No, here also.
So there you're using laser, correct?
Right.
But here we are using microwaves. So microwave, let us say 28 gigahertz. Okay. So lambda will be in the centimeter, correct?
Right.
And you can see that this whole structure from here to here is only maybe around 10 millimeter or maybe 1 millimeter only. Okay.
Okay. Okay.
So when I shine microwave,
Mhm.
so technically this microwave going to expose everything.
Right.
So it's not like a pinpointed laser. It cannot go to the single ion or electron in
So
this
in
case.
your operation, you mentioned only one electron can be
Yes.
flipped, right? So how do you
Yeah.
achieve that?
For that one, actually what we do, I can show you one picture. Yeah, here. I mean, so this is also I'm discussing in the class here, but what we do, we make many rings. Okay. So central ring, let us say on the negative potential, correct? Then we make one more ring here. Okay.
Mhm.
That is actually made of a superconducting material.
Mhm.
Then another ring may be a positive potential.
Mhm.
Now what we do, we pass some current in the superconducting ring.
Mhm.
And because of this persistence current flowing through the ring, okay, what happened that if there is no current flowing in this ring, the magnetic field will be uniform, correct? Here. The magnetic field I apply is uniform, okay?
Yeah.
But once I apply the current in the loop, the magnetic field will distort, correct?
Mhm.
Because the current is there. So this is not going to now allow the field to pass through, or it will change the field pattern. And this is the reason that this kind of field pattern you're going to see.
Mhm.
And electron is there, correct?
Yeah.
And this electron spin transition state, okay, this depends upon 2 mu p and b, correct?
Mhm.
So if the magnetic field changes,
Mm.
so that's going to change the spin state, correct?
Right. Right.
So this I can do individually, am I right?
Okay. Okay. Got it. Yeah.
So although microwave is shining everywhere, okay,
Okay.
but let us say if I detune one trap,
Got it. Got it. Yeah.
okay, so even if this is going to see that 28 gigahertz frequency, but
Right.
since this gap is changed, it will not respond.
So it is tuned to only that particular.
Exactly.
Okay. That's nice. Yeah. Good. Yeah. Yeah. So another confusion, like so today for calcium, the ion trap, and for this particular your device that you're coming up, so we have this vibrations also coupled, right?
I mean, let me clarify. We are not working on the calcium ions. We are working on this one. Okay.
Okay. Yeah. Yeah. Got it. So my confusion was, so can we not work only in the ground state? Why do we, we have this vibrational state? Of course, it is unavoidable. We understand, but
But okay. For example, think about that. Um how you going to couple two qubits? Okay. So there's a
okay.
one qubit here and another qubit here.
Okay.
So if I want to couple them, I need something. I'm right. So because let us say even if you talk about electronic state, okay, so I can put this in the S or D, correct?
Right, right.
Or I can put in the one state or a zero state. I can put another calcium ion in the 0 and 1 state, but they're isolated qubits.
Right, right.
So finally, when you're going to create a let us say gate, then I want two qubits entangled, right?
Okay.
And entangling can be done only if there is a some kind of link between them, right?
That is a vibrational
That
coupling.
is a vibrational link, exactly.
Okay, okay.
That's why we need a second motion or second type of quantum states, okay, which is going to use here to entangle these two states. So when I was discussing the quantum theory of the qubits, I never talked about how to entangle two qubits, okay?
Right, right, right. Yeah.
I just mentioned that okay, two qubits are entangled.
Yeah,
Okay,
yeah, right,
but
yeah.
quantum practically you need something, okay,
Okay.
which can connect these two qubits. So here is the vibrational motion, okay, of these two ions, okay. So they couple them together.
Sure. Okay, that makes sense. Yeah.
Yeah.
Thank you. Yeah.
And this is our actual team who is working on developing the quantum computer at IUAC. I think many of these people are maybe known to you. So at IUAC, me, Dr. C.P. Safwan, and one Kedar Mal, and Dr. Anup Chaudhary. So we are the 4 people from IUAC, and they have a different expertise. So Kedar Mal, he's also doing his PhD on the quantum computing part, and he's actually on the simulation part, mostly on the simulation part. Dr. Anup Chaudhary, he's on the dealing with the cryogenic part. And then Sadiq from the Bangalore, Professor Ravi Shankar, he's our theoretician, helping us to deal with the quantum error corrections and the decoherence. Then we have some international collaborations also. For example, Professor Vardu, he's from the Sussex University, London, and he's working on the trapping electrons in the panning trap, but cylindrical panning traps. Okay, so he's helping us a lot. Then Ferdinand Smith-Kahler, he's from the University of Mainz, and he is working on the calcium ions. Okay, Paul trap based. Then these 2 guys from the Germany, so they are expert in the ion traps. They are part of our group. And this person, they are 2 people, are theoretician from the Italy. So they are ion trap theoretician. And the Stefan Stahl, he's an industrialist person, but he is actually helping us us in the instrumentation. So this is our overall group at which is involved in making the quantum computer at IUAC. So in this short span of time, this was the only, I think, this much. I mean, we would have been better to discuss more, but I think we can stop now here regarding the hardware part. And tomorrow we will talk now only regarding the programming and the Qiskit. But before I talk about the tomorrow, if any further question, if you have, please let me know. And I have one slide here just to show. Maybe you can. I'll try to think over it. I mentioned you that in the case of superconducting qubits, these qubits are nothing but excess of the Cooper pair or no Cooper pair. Okay. So similarly, the flux can be used. So you can think about different types of situation which is quantized, and that is but quantized but causing real change in the energy. Also keep in mind, if the 2 systems are there, like let's say head and tail, but if this head and tail not causing any change in the energy, okay, then you can't use them for the quantum computing. So if you have a 2 states, quantized states, and these 2 quantized states causing some physical change in the energy, then those 2 quantum states can be used as a qubit. And very interesting phenomena in the nature takes place in the photosynthesis. So in the photosynthesis, you can see carbon dioxide, water, okay, and sunlight. These 3 inputs are taken by the plant. And in the plant, then you can see photosynthesis takes place, and you end up with the sugar and oxygen. Biomass produced. And inside a mechanism, people trying to understand that when the light hit this chlorophyll, then it produces electrons are excited, and it is going to produce excitons. Okay. So there are many chlorophylls in this leaf, and at each chlorophyll, you get excitons. No. And very interesting thing happened here, that there's a one energy center, and all these excitons produced at each chlorophylls, somehow they are creating a coherence, a quantum superposition. They are in the coherent state, and every excitons reaching to the reaction center. So let us say this is a reaction center. So the excitons are produced everywhere, and somehow they all end up at the same position. And there is 100% efficiency. I means no excitons are lost in this process. And this is only possible if there is a coherence between all excitons. And this must be a quantum coherence. And this process is happening at a room temperature. So you can see that this quantum coherence somehow taking place in the photosynthesis process, even at a room temperature. But at the moment, we are not, our scientific community, not able to understand how this photosynthesis process actually taking place. And this is the reason that we are not able to create artificial photosynthesis. Maybe the quantum computers we are making, that may help us to understand this phenomenon. Or maybe if we can understand the photosynthesis process before, then maybe we will be able to create a quantum computer working at a room temperature. Something different quantum states are working here, okay, which are able to create a coherence even at a room temperature. Maybe you can think about it, okay? It will be a game changer altogether. So that's all from my end. So maybe we can have some discussion or questions if you want to ask.
Tomorrow is a holiday, right?
No,
Sun-
tomorrow is the last class because tomorrow we're going to discuss this Qiskit and the IBM platform.
Oh, the schedule mentioned break,
Yes,
so I
yes.
got
Okay. So tomorrow you will be having one. Let me now clear here that for tomorrow timing, I will also post in the WhatsApp group from 6 p.m. to 6:30 p.m. We will be going to have a quiz number 2, and 6:30 to 8 p.m. we will be have this IBM and Qiskit. And for this one, I have requested one faculty, very good faculty in the quantum computing. Okay, Vandana Luthra. Okay, so she will take this class on the IBM and the Qiskit tomorrow. So I will get at least one day rest. But there is time schedule. I will post also in the your WhatsApp group. And this slide, which I'm showing that we are still in the vacuum tube era. Okay, maybe the day we able to produce or create those quantum gates at room temperature and with with the much easiest way to create them and still remains coherent and entangled. That day, I think we will be enter into the new regime, or maybe, for example, from the vacuum tube, we enter into the diode base. And same way, we will be moving from the big quantum computer to a small quantum computers, something like a photosynthesis. So that's all. Yeah, any comment or question? So Jabin, shall we close then?
Yeah, I think Sugam, yeah, we can close it
Yeah.
if there are no other questions.
Okay. Okay. See you then tomorrow.
So can you stop recording?
Yeah.